Okay, I think just I think we can start now. So let me do a quick recap of what we did in the last class. So this is one example that we took. The set of all second order polynomial, and I did a mistake in the last class. How many of you recognize that? I had emailed also, right? What is that? So if you look at the following, right? So let's say the set of all polynomial, which is a naught plus a1x plus a2x squared, such that a1, a2, a or a0, a1, a2 belongs to R is a vector space. That is something that we verified in the last class. But then we looked at the notion of basis and so on, and that's where we made a mistake, right? So since some of the people who were online, I couldn't. They couldn't connect. As a result of which, they lost some part of the last lecture. So maybe I'll do a quick recap so that they will also understand what certain notions that we discussed yesterday. So, what was the first notion that we discussed yesterday? What is the first thing that we did, right? After looking at vector space, we looked at what is known as linear independence, right? Is that correct? Right? So, what do you mean by linear independence? So essentially the idea was this, right? So suppose I take two vectors like this, let's say v1, v2, right? These are linearly independent because I cannot take a linear combination of the two and get 0, right? Whereas, for example, if you take a vector like this, right? So v1 is this, and let's say v2 is this. Now I can take a linear combination of the two to get 0. What is that? Take for example minus v1, that will be this direction, right? Minus v1. So I have to add v1 to it. So v2 I can write it as what? Or v2 I can write it as some alpha times v1. Of course, in this case alpha is less than 1. You are shrinking the vector. So now all that I have to do is v1 minus alpha, or let's say v2 minus alpha v1 is 0, right? That means 1 times v1 plus minus alpha times, 1 times v2 plus minus alpha times v1 is 0. So some linear combination is 0, right? That's what linear independence is, right? So how do you define that? We say that v1, v2, etc., vm belonging to v are linearly independent if you take any linear combination, right? If summation I equal to 1 to m alpha I vi equal to 0. Suppose I say that some linear combination of these equal to 0, that implies alpha I equal to 0 for all I, right? I mean, the only possibility is all the coefficients being 0. Otherwise, you cannot have this, right? This is linear independence. What is the next thing that we looked at? Span, right? What is span? So we looked at this example, right? So what is the span of this vector v? You take all possible linear combination of this vector. What do you get? You scale it by some positive constant, then you get all the points in this direction, right? Till infinity. If you scale it by negative, you'll get all the points in the negative direction. So essentially, you get a line passing through the origin, right? That's the span, right? For example, if you take this, what is the span of this? You take any point in R2, I can write it as a linear combination of these. In some sense, I'll get the entire R2, right? If I take, for example, V1, V2, V3, what will be the span? Same thing, R2, right? So, what is the span? So, we'll define span of some vectors. So, span of V1, V2, etc., Vm. So, these vectors V1 through Vm need not be linearly independent, okay? So let me just check. Okay. Need not be linearly independent. Regardless of what kind of vectors you pick, span is defined. So what is span? It is all possible linear combinations I equal to 1 to m alpha I vi such that all 5 belongs to R. You pick any set of m numbers, take the linear combination, you get a vector. Keep on doing that until whatever you exhaust every possible combination, right? So that will give me the span. Is this fine? Now with this we define what is known as basis, right? So what is basis? So the idea is I have to write a given vector as a linear combination of some set of fixed vectors, right? That was the idea. We started with that. So you take, let's say, n vectors. Okay, so let v1, v2, etc., vn belong to v. Okay, we or okay, we say that v1, v2, etc., vn forms a basis of v if, what are the two conditions? What are the things that you need in order for this to be a basis? What is the first thing? Louder. It should span the entire vector space. In other words, you look at the span or all possible linear combinations, it should be the entire V, right? And what else? Of course, in R2, on a plane, I can take 100 vectors, okay, pointing in different direction. It will span the entire R2, right? There is no big deal. But we cannot say that those 100 vectors form a basis, right? So only 2 vectors can form a basis. So what do you mean by that? So V1 through Vn or what? Linearly independent, right? So this is fine. This is what we did in the last class, and we saw that the set of bases need not be unique, but this number n called the dimension should be unique. Okay, so let's maybe revisit that today. Okay, so I'll start with the definition. Okay, let v1, v2, etc., vn be a basis for v, then the dimension of v is n. Okay, so this is the definitions. Now I need to prove that this number n is unique, right? So I cannot have two sets of vectors. One, let's say one is, there are n vectors, the other one m vectors, such that both form a basis, right? It's not possible. So towards that we need what is known as replacement lemma.